Welcome to the second video on Introduction to Quantum Field Theory. Here is going to be a very short video just talking about types of fields and how to visualize them. There are some useful definitions that we're going to have before. So this right here, at least in this video particularly, M will denote the subset of the vector space R13 that corresponds to position. This is kind of, if you're a mathematician, you'll agree with me, this is kind of an inaccurate notation because M, it would just be the entire vector space here. But the point I'm getting at here is that when I'm using M here, I am meaning that every vector in R13 will be considered as a position vector. So any vector in here, so this vector space really is this vector space. But what I'm saying is that any vector in here is considered a position vector, whereas typically any vector in here could be, it could be momentum, it could be the wave vector, it could be electric field, magnetic field, blah, blah, blah. But here I'm just saying if there's a vector in M, then it's considered a position vector, even though the vector space itself is equal to R13. But yeah, I agree that this notation is kind of misleading, but you get the point what I'm trying to say. And also, this k right here is either equal to the real numbers or to the complex numbers. This just means a scalar algebra, and the scalar algebras are either, or at least in the case that we're interested in physics, it's either the real numbers or the complex numbers. So when I write k, it can be either r or c. So the most important fields in physics are scalar fields, vector fields, and spinor fields. Generally speaking, a field is a mathematical object that assigns some number, vector, or spinor to every point in spacetime. So a scalar field, a scalar field is defined as a map B from Minkowski space to some scalar space, which is basically saying that you take a position and you map it to some scalar, which depends upon the position. This is the definition of a scalar field. For a vector field, it is, I'm just going to take this, copy it, and paste it. A, which maps from M R13, and R13, of course, R13 is basically, it's basically me saying that you're mapping it to a vector space where this vector space could represent anything. It doesn't just have to be a position. And of course, you're mapping to a vector. And then for a scalar, or for a spinor field, you go from here, lowercase c, so technically, um, could also use C4. We will see later that we could use C4 as a preview. A a spinor field that maps from Minkowski space to C squared is basically a Weyl spinor or a two-component spinor. But for a Dirac spinor, which is the sum of two Weyl spinors, then if you have two Weyl spinors, then you have two extra components, so C4. And this is just the mapping of the position to some spinor value. So these are fantastic mathematical definitions, but they might not help with visualizations much. So I have a drawing. I was going to redraw it completely in my notes here, but I just didn't want to. So I took a picture from my script instead. So the idea is that you can visualize space-time. You go two dimensions lower. So space-time is, of course, one dimension of time, three dimensions of space, so four-dimensional. But you can imagine Minkowski space-time as some kind of sheet, flat sheet. And then fields are sheets superimposed on it. So Minkowski space is here. And then for a scalar field, at each point here, you go up and there is a corresponding scalar. And I've represented the values of the scalar with how big the circles are. So big circle means big number. And so you can imagine this going here. This could be like 100, and then go here, and this would be like 2. So much bigger than here. And this would be a scalar field. I also drew a vector field up here, where at each point here, there is a vector pointing in some direction. So like going here up to, or let's go here to here. You can see that there's a vector pointing that way. Going from here to here, there's a vector pointing this way. So there's a vector at each point pointing somewhere. I actually, just for the sake like of demonstration, I wrote this vector field as the gradient of the scalar field. So it actually shows where the field is going. And so because of this vector field actually corresponds to the gradient of a scalar field. And this is something that actually, this relationship comes up a lot in physics. So I did choose this for a reason. For example, like if you want to describe the electric field, you can describe the electric field in terms of a potential. And so you would have a scalar potential, like voltage, and then the gradient of that would give you like the electric field. So yeah, those are the drawings. That's how you can visualize fields. You'll note that I didn't write one for spinor fields. That's because spinors are a little more complicated to talk about. If you're familiar with geometric algebra, then you know that a spinor corresponds to something called a rotor, which rotates an object, which rotates specifically the vector. So in geometric algebra, a spinor is the object that rotates the time-like vector, so the vector going purely in the time direction. The spinor is what rotates that time-like vector into the Dirac current. And the Dirac current is it's its own thing. It's the current of probability density. And so that's what a spinor is. And so you would imagine that at each point in space-time, there is a transformation that corresponds to that. So that would be kind of how you could visualize a spinor field. In non-relativistic physics, so if you were to imagine a spinor field of Pauli spinors, you could imagine them as vectors themselves, actually. I have a video of that on my YouTube channel, Eccentric, which makes videos on geometric algebra. So there are different ways. Spinors are more complicated, so I didn't want to write out everything, but if you are interested in that, stick on this series because we'll talk about spinners more and also learn about geometric algebra because geometric algebra has the most natural description of spinners that exist. Now, one more thing before I finish this video. I want to talk about what's called the field space. And what that means is how many components you have. So, for example, here, if this scalar space is just a real number system, then this scalar field would have one component. But if this were the complex numbers, this scalar field would have two components because in a complex number, you have two components. In what's it called? In R13, which is the vector space of 1, 3, there are four components. So a scalar field can have either a one-dimensional field space or a two-dimensional field space. And then this has a four-dimensional field space. And then if this is a Weyl spinner, then it's a four-dimensional, because four times two, four-dimensional field space. Or if it's a Dirac spinner, then it's an eight-dimensional field space.